Good morning and good afternoon, maybe, and it depends on the time and time difference. So welcome to the session. And welcome to the first international high-level forum on smart and autonomous navigation technology of SIP. So today, I'm Etsuro Shimizu, professor of Tokyo University of Science and Technology. So today, I'm assigned as a chairman of this session. And sorry, I don't have the information about the co-chair from the Wuhan University of Technology. So maybe later, I would like to ask the introduce by yourself. Anyway, so time has come, so we would like to start the session, today's session. Is that okay? Especially for the presenter and associate professor from the Wuhan University of Technology. Liu, is that correct?
Yes.
Professor Liu?
Yes, can you hear me?
Yes, so
okay.
Please start your presentation.
So,
thank you. If prepare the presentation.
So I suppose that you can see my screen now?
Yes.
Okay, thank you very much. So
yes.
Good,
yes, please.
Good day, ladies and gentlemen, online and offline. I'm Dr. Julian Liu from Wuhan University of Technology. And it's a great honor to be here sharing our research and perspectives for virtual real interaction testing of intelligent ships. So I'm Dr. Julian Liu from Wuhan University of Technology. So today I will give the speech in 5 parts. First of all, I would like to share some information about the state of the art for intelligent ships and some progress for testing of intelligent ships. And the third part will be research on the testing for intelligent ships, what we have done and what our colleagues worldwide have done for this area. And the fourth part will be the development of our in-house system for testing. In the end, I will share some summary and perspectives for the future. So first of all, before we talk about intelligent ships, I would like to say a few words about shipping, because as we all know, that shipping is actually the background for ships. We all use ships for transport cargoes, and without a good shipping environment, without a strong demand for cargo transportation, we don't need any ship. So what would we expect for the future about shipping? We say that it will be green, intelligent, and resilient to be safer. And it's to some degree, it's a common perspective worldwide, like our colleagues from Europe, some projects like AEG's November or Moses, this kind of projects were supported by Horizontal 2020 from the European Union. And in China, we developed similar intelligent shipping projects for inland vessels, for inland shipping, near coast shipping, and some coastal areas. So from our university, Wuhan University of Technology, we expect that we need to develop a new generation of the waterborne transportation system. Like I said before, it should be green, intelligent, and resilient. We would like to expect that we share all the data among the ships, ports, terminals, and we break the barriers between all these systems. We have to merge them all instead of setting up different small percentage of the systems. And with the expectation for shipping, we also have to know why do we want to develop intelligent ships? What are the driving forces behind these technologies? Let's say that we would like to develop intelligent ships to increase the interest and decrease the cost. We build ship or we increase shipping to earn more money, to develop transportation, to develop the industry. How can we reduce the cost and how can we remove people from ship side to the shore side is something we need to do with the intelligent ships. In the future dream or in the future development, we would like to move people from shore side to the from ship side to the shore side to give the people to start a better working environment. And by doing so, we have to use remote control technology, etc., etc. If we can move some people from ship to the shore, we can reduce the physical space, like the hospitality, like the living area of stuff, so we can have more space to transport more cargoes. As long as we can transport more cargoes, we can earn more money, make more profits for the shipping companies, industries, and so on and so on. On the other hand, if we can have a better transportation system, like better shipping system, we can optimize the dispatching strategies to optimize the whole logistic chain, to increase the usage of the waterways, the usage of the ships, and improve the whole logistic efficiency. All in all, we would like to reduce the cost and the stuff by using remote control technology. And on the other hand, we would like to increase the interest by reduce the cost and have more space, transport more cargoes with a higher transportation efficiency. The keys to intelligent ships we summarize as the navigation, energy, propulsion, and testing. We have to use green energy and better electricity propulsion to have better control of the ship. And of course, we have to use the intelligent navigation to reduce the human labors and to move people from ship to shore. By doing so, all the equipment, software, hardware, all those kind of things have to be tested. And that's what I'm going to tell you about the test and verification for this kind of software and hardware. Worldwide, all the researchers in this field are actually quite fancy about these nice, beautiful ships for the future, remote control, autonomous control. Our colleagues from worldwide, like Belgium, Finland, Japan, Korea, South Korea has done a lot of work for different type of ships, different scenarios. And so what have we done for testing of these kind of ships? Some work have already been proposed by IMO, like the guidance for mass trails. And for mass trails, we have to be safe, first of all, and we have to do some communications between different joint parties. With the IMO guidance, a lot of test beds have been constructed worldwide in different countries, different areas, different sizes. And in China, we also have a lot of test sites in Zhuhai, Qingdao, Dalian, and so on and so forth. And yesterday, a nice presentation was given by Professor Kim from Korea, for the autonomous surface ship project, CAS project. In the CAS project, we have a nice project structure, and they propose about the virtual simulation test bed and the sea test bed for both for virtual simulations and for real practical applications. But testing is not something new. It's already something that has been done by for the autonomous cars. Because nowadays we have like a Waymo, Tesla. In China we have Apollo, Huawei. A lot of the companies, they are doing some tests. But we have to know that we also have to learn some lessons from the testing for autonomous cars, because field tests, I mean, by using real cars to do the test, is fundamental, but it's not everything. It doesn't suit for every cases, because you may have a million cars with the same size, with the same branch, but you cannot have similar ships. Each ship is actually different in different scenarios and different cases. We learn a lot of lessons from testing of autonomous cars, automated cars. We have to set up scenario-based testing, functionality-based testing, which means we have to design some scenarios for different perspectives, like navigation or collision avoidance. We also have to design some functionality-based testing. If you want to test a function of a radar, or you want to test the function of a controller, and such as such. So we also learned some lessons from the NOVAMAR project, which is supported by Horizontal 2020 from the European Union. First of all, they proposed this new vessel chain concept, which means they would like to use 3 ships or even more ships in a group to transport more cargoes like a chain. After this propulsion of the concept, some virtual simulation were done by Marin and also some other partners with this kind of software in the loop or hardware in the loop simulations. Afterwards, some model scale tests were done by BST in German, and this model scale ships were tested in the towing tank, and as you can see that the 2 ships were following each other. So in the end, the Noemar project run some full-scale tests with some cargo ships and one cargo ship with another cruise ship. So all in all, they proposed the concept, they set up some simulations virtually, and they also do some physical tests with model scale models, and in the end, they run some full-scale real ship tests. In the third part, I would like to tell you something about testing for intelligent ships, what techniques or what softwares, what hardwares we need to use for testing. In China, at least our group, we focus on, we do the testing based on the rules for intelligent ships 2020, proposed by China Classification Society, the CCS. They have already set some functions or requirements for different functionalities of intelligent ships, like smart navigation, remote control, or autonomous control, etc., etc. That is the foundation for our testing. We also have some challenges and problems for testing. How can we secure safety? Because you may test a ship with some software that you don't know, and how can you guarantee the safety of your own ship and the environment around your ship? How can we improve the efficiency of testing? Because real ship testing can be really, really expensive. We also have to reduce the cost and increase the coverage to guarantee all the tested scenarios, different ships, different ship types. We also to improve the reality or fidelity of your simulations. We also have to consider some emergency considerations. If something goes wrong, what should we do? With all these challenges and expectations, we have to think what technique do we have nowadays. Technical challenges are, well, we have like the virtual simulators proposed by Kongsberg or Wachla, in previous time it chances, or we can do some tank experiments like the Yarabek plant, which was done in Norway, or field test. Also, Yarabek plant had done a lot of work there. Also, some real ship experiments which were done by NIK. So, simulators, towing tank, field test, or full-scale test, those are the tools we can use for testing. But each tool may have its own pros and cons. So, we propose some concepts. How can we do the testing for intelligence? First of all, you have to do the test. It's something 0 or 1. Do you have a real function here, like a cost planning, cost keeping, avoidance decision? If you have it, if you have this function, it's 1. If you don't have it, it's 0. So on the other hand, if you have a lot of functions, all these functions can be merged together to form some task level functions. You can merge cost planning, cost keeping for autonomous navigation, etc., etc. Moving forward, you have the method level. If you want to fulfill the task, you may have some maneuvering models, cost planning algorithms, control algorithms, etc., etc. You have to verify this method. It's a yes or no question. Furthermore, you have to evaluate or do the evaluation. Is that good or bad? Is that smart or not smart? So for the performance level, you have to consider the algorithm accuracy, the functional switch, navigation safety, efficiency, etc., etc. So here in Wuhan, we propose virtual real interaction testing because, like I said, each virtual simulation or full-scale test may have its own cons and pros. So we expect that we do 10,000 times virtual simulations, run 100 model skill tests, and in the end, we run one real ship test, and we merge all the information and data we generated during these simulations or tests, and merge them together to have this kind of 1 million virtual real interaction tests. But we have to consider what do we test and what we don't test. We may focus on the autonomous navigation system and the communication, the internet communication network. We test the software and the hardware during the navigation areas. We do not test the parameters of the sensors. The limitation of this sensor will not be tested. We won't test the human factors in this kind of operation. So in the first part, I would like to tell you something about our in-house system for testing. There are a lot of words here, but all in all, we would like to generate 4 scenario libraries for typical ships, typical natural environments, and navigation areas, and some navigation behaviors libraries like crossing, overtaking, etc., etc. We would like to build up some test beds, like a virtual test bed, model skill test bed, full skill test bed. We also like to construct one platform to merge all these scenarios and test beds. So this kind of components or structure for our system. You have different ships, different environments, different nature, environment, wind, current. You have like the strait gauges or near shore, coast, far sea, and you may have some different behaviors, crossing, overtaking, and you have different test beds. You can use different test tools, and we develop our own models, our own navigation system to modelize this system to connect with other softwares. You may use different software in the loop, hardware in the loop, human in the loop, testing methods, and you run some evaluations, and you display your results. This concept of components of our system. How can we do that? We have 6 steps. First of all, we would like to build an in-house software to run the autonomous navigation. So we develop the system from maneuvering modeling. You analyze the hydrodynamics, you build the micro models based on which you know the forces and you know the motions of the ship. We design the structure of the functions. You have to use some data from the ship and the weather. You design the controller and the collision avoidance system. You have the PLC controller to connect your system with the actual propeller and the rudders. We also design some route planning and efficiency or evaluation for long path evaluation, like the weather routing, etc., etc. You have to consider the fuel consumptions. And we analyze a lot of different control methods, like the traditional PID or MPC methods. We also use some neural learning based, like this one, like the learning based MPC, or some Koopman operator, or dynamic model decomposition, all those kind of learning neural network. So with different control methods, we can also do some collision avoidance among multiple ships, because 1-to-1 is easy, but 1-to-3, 1-to-4, or 2-to-2, all those kind of scenarios are quite challenging. This is something we do with the transport simulator. This is a ship running through the Suez Canal. We use the transport simulator to provide the mathematical model for the ships and also for the visualization. But the ship is controlling by our autonomous navigation system. Let's say it's running. It runs smoothly. It can still pass the Suez Canal with multiple operations. And this is something we analyze the result. As you can see, we still have some pitfalls for the system. The speed of the ship decreases, and we use multiple rudder angles, like 4 times than the real captain do. So we control the rudder like 200 times, but a real captain will only use like 50 times of the rudder. So the system is not just smart, but it's functional. Second part, we have to analyze the testing scenarios. For testing scenarios, we can set some testing scenarios based on the exhausting method. You can raise all the possible areas. You may also set up some extreme scenarios. You may set a scenario based on navigation practice. And we have to select, make some drawings from this kind of scenarios. This is some scenario we build with Unity 3 for with visualizations, like some open sea or the towing tank in Wuhan or university, some inland testing scenarios or offshore testing scenarios. We can also build kind of this digital twin virtual ship. And this is the model scale ship. We have this kind of simulations can be performed with our Unity 3D in-house software to develop these simulations. We also have some scenarios set up based on the real inland waterways, like somewhere in the Yangtze River, you have the ferry line, you have the bridges, you have the larger angle changing, and we can use also the Transas NT Pro 5000 software to run these kind of simulations. And another case is for the harbor entrance and the docking and undocking. You have junctions, you have the disturbance jet flow. This is also quite challenging. And we can perform this kind of simulation to see if you can control a ship into the harbor. So after the scenarios, we have developed testing tools. We analyze a lot of different ship types with inland vessels, ocean-going ships, tankers, cargo ships, containers. We build the mathematical models to provide the motion predictions, and for simulations, we have this kind of Transat marine simulator for full mission simulations, and we have a full benchmark ships for different types of ships, different scenarios. And in the end, we have to verify the methods. We constructed a lot of different model scale ships. We have 5 ships for the tankers, for inland containers, for ferry boats. And we have the tugs, inland containers. This is something we do in the pre-running tank in our university. We run some model scale simulations or model scale tests in Nanjing. In Nanjing, the Qinhuai River is a famous interest place in Nanjing. We do this kind of docking and undocking on autonomous navigation test for model scale test. We also have to propose the evaluation method for to compare your system, the software, with the human. Is your system smarter than people or not? So it's a qualitative evaluation. You also have to compare your system with other people's system. Is your system better than the others or worse than the others? We have to use some kind of evaluation method to give a score or a result. How much score can you get? We propose this kind of Turing-based evaluations is something traditional or traditional for testing an AI. In the end, we propose some demonstrations like this is a PhD student in our university, in our group. He is driving a ship through this waterway, avoiding other ships. If he can sail this ship safely, he is a good captain. If our system can sail the same ship in the same environment safely, the system is roughly okay, or at least is okay for this scenario. That's something we do in the end for this kind of virtual real interaction testing. And this is also something we do with the simulator. We use different test scenarios for docking and undocking. We use something like the ship's vessels entering the lockage. You can also test your algorithms to see if you can do this job. And we can also maybe perform some kind of formation control test. You have different boats, and how can you test your algorithm is also something nice we would like to do. And in the end, we still have a lot of pitfalls. All those right points are something we are worse than the commercial system, but we also have some flexibility compared to the commercial systems. All in all, we have already had some good results, some publications, monographs, and a lot of PhD students and master students are working in this area. We are supporting European Horizontal 2020 project called Safe Mode. Use our system, we will run some tests for operator assessment of remote control ships. And this is the last slide in my presentation. We have some experience. if you want to test your ship, you have to know how to design and construct an autonomous system. It's strongly connected to each other. If you don't know how to design the system, you don't know what you would like to test. And in the end, the testing for the researcher on testing, we have to clarify or answer the question: is your system safe enough to drive a ship? And how much work can the system do for human? And we are experiencing a lot of opportunities, because nowadays we all want ships to be green, intelligent, and safe. So there are a lot of work to be done. We have a lot of new research areas like remote control, unmanned control, autonomous control, ship-shore coordination, formation control. A lot of work has to be done. And testing is something really connected with our R&D and device design. And in the end, we also have a lot of challenges. There is a lot of work to be done for testing. We need a lot of time, a lot of money to be invested in this area. There are a lot of difficulties in modeling, testing, scenario definition, scenario selections. And we also have a lot of difficulties with communication and collaborations. We have to understand other parties, how do they design their system? How do they think about the autonomous systems? And that's all for my presentation. If you have any question, I will be happy to answer that. Thank you very much.
Yes, of course. Thank you very much for your interesting presentation, Professor Liu. So, any question, comments from the audience? Please raise your hand, Mark, or turn on your mic or something like that. Let us know that. Also, about the questions? No.
No.
Okay.
Okay. If you have any,
sorry.
you can contact me.
Sorry.
Email.
Excuse me, Professor. So, and from the one person and raise a hand. Yeah, so please turn on your mic and picture or bot. Yeah, yes, please.
Good time of the day. Thank you very much for your very interesting presentation. I was just wondering, how many test scenarios do you believe are necessary to be run in a simulated environment to consider that we have a safe system? Thank you.
Okay, I think you are asking about the scenarios, how many scenarios we may have in the system, right? Actually, we have, how to say, I cannot give you an exact number because we design the scenarios for different purposes. Actually, we have two kind of systems. One is with unities ready for visualization we developed by our own. So in this system, we have like 6 or 8 scenarios. These are 4, and these are another 4. And for some scenarios we constructed with the translator system, there are hundreds like that. We can set up the scenarios as we expect. So actually, there are a lot. Hopefully, I answer your question.
That's okay. So I think that so I have one question to add that his comment. So from my point of view, and maybe in your point of view, that so how many scenarios do we need to carry out to the test and prove the system, the systemability for that? We need to test to check the autonomous system and the collision avoidance system.
Thanks for the question. I think it's at least from my consideration or perspective, I would like to expect at least one or 2 full-scale experiments as the final stage for tracking a system. But before that, we would like to do like at least about 10,000 simulations virtually with simulator or with in-house system. And you may reach like 10 to 100 model skill tests to verify the results of your simulations and to connect the data from virtual simulation to full-scale experiments. So one full-scale experiment, 10 model-scale experiments, 100 or 1,000 or 10,000 virtual simulations can be sufficient for testing an autonomous system. That's something I think. Yeah.
Yes, thank you very much for your comments. So, okay, almost the time has come. So thank you very much for your wonderful presentation. So next, we would like to move to the next presenter, Professor Zhou from the Harbin Engineering University. Please prepare your presentation.
Okay, good afternoon and good morning. My name is Zhu Qida, comes from Harbin Engineering University. Very glad to have the opportunity to give a brief introduction about our work for Smart Ship. The leader of my group is Professor Xia Guihua, the Vice President of our university. And 3 parts in my report. The first, I will introduce a simulation platform. Consists of some blocks. First, we will develop some scenarios for the intelligent function. And once we select the scenario, the system model will be driven by the initial condition of the scenario. The system model includes the ship, engine, sea state, meteorological model, etc. And the output of the system model can be derived the sensor model. It's a significant feature of the system that some sensor model has been developed. The output of the system model, sensor model can be used as the input information of the intelligent function.
Excuse me, could you share your slide? Because my slide screen is too small for that. That's only for me. Everybody can see the slide.
Yes, it is. It appears to be visible for me. Perhaps it is only in your end, Professor Shimizu.
Okay. Yeah, thank you very much. So I'll do that by myself. Sorry that.
I will continue. Significant further, we have developed some sensors model. The output of the sensors model can be directly used for intelligent system. Seeing that the intelligent function is realized by the situation awareness on board autonomously through fusion of the sensor measurement. So I think it's more effective for evaluation of the intelligent function. Okay. The simulating platform can support some intelligent function. Here we only consider autonomous navigation, efficiency, energy efficiency methods, and operating and maintenance board diagrams. Okay. This is about the whole system, simulation system. There's the bridge, just the same as the real ship. And you know that the accuracy of the model is very important for simulation system. So we have collected a large amount of CTOs and the watch data of the ship to be simulated to optimize and update the model to increase the performance of the simulation. Okay. This data is from CTO. And some models I will introduce about the sensors model. First is the Ais model. The information of Ais comes from the scenarios and just translate into the data format of the Ais is okay. Next, there's a radar model. Radar model, the simulation. We select the pentagonal, outline to describe all the shape simply, and the scan beam is coincident with the x-axis of the initial frame, and can simplify the problem from the two-dimensional problem to one-dimensional problem. Then we can simulate radar measurement results. The number of echoes is determined by the length, the width, and the relative heading of the object shape. This is the model of the radar. And this is about LiDAR model. LiDAR model, we use small triangles as the basic unit to model the surface. We use many triangles to model the surface of the shape. Then we can calculate the interaction between the laser beam and the triangle's planes to get the point cloud of the object shape. We also need to define some frames, and the point cloud is described relative to the shape's frame. Okay. This is a camera model. A three-dimensional display model of the environment is developed. It can be directly used for the camera model. We use a 12 camera to consist of omnidirectional vision system. This is some result of the evaluation of the intelligent function for automatic navigation, energy consumption, etc. Okay. The second part, I will introduce some test equipment developed by our team. The first is omnidirectional vision system. We use 12 camera and 12 infrared camera joined together like this. We have designed a special embedded system for image acquisition and processing. This is the final omnidirectional imaging after stitching. We can see that stitching algorithm need to be continue update. Okay. There's some application algorithm and the programs are developed based on the panoramic vision system, the object recognition and the classification, and image enhancement algorithm for rainy and foggy days. In some, this the continuous work about image processing. Another equipment is about LiDAR, panoramic LiDAR. We use a LiDAR with 128 lines. The angle in vertical angle is about 12 degrees. The range distance is about 2 nautical miles. With a 2-layer receiver. We use more than 2 years to develop the system, and not just in testing stage to test the performance of the system. And at the same time, we have developed software for object detection and classification under the point cloud. And this is another kind of LiDAR system with a narrow view angle, only 2.56 by 2.56 degrees, and with 64 lines. The ranging also 2 nautical miles, just in testing. And this electrophoto system combined together, we can realize more detailed object detection and classification. Okay. Another important equipment that we had built up a new ship. This ship belongs to our team. Some advanced device, for example, fatal differential positioning system, optical fiber INS, DP system, fabrication, active reduction system, engine fault diagnosis system, and the situation awareness system, service control center, and autonomous navigation system. All the system is developed by our university. Okay. And the ship with use a new type of propeller. This AC motor. The outer as is just the stator of the motor, and the propeller is the rotor of the AC motor. A new kind of propeller. The efficiency can be improved by reducing the draw line. I think that the remote control method is a more effective control mode of today. So we have built up 2 remote control center. One is located in Qingdao campus and another in Harbin campus, 2 remote control center. And with 2 harbor and docks in Qingdao and Yantai can provide test circumstance. Okay. The third person, very interesting problem is about the control algorithm. We have this block is about adaptive control, hiding adaptive control. It's a structure of a hybrid model reference adaptive control and self-tuning control. Here shows the result of the controller head keeping and head changing. Statics about the result, about accuracy, rather angle changes and under different state is a effective controller. But there's a very there's a difficult the difficult in adaptive control is the model estimation, auto estimation. The may depend on the persistent exciting ability of the system signal. If the persistent exciting ability is not strong enough, the adaptive control will fall. And the model parameters and the control outputs will diverge. So there is a contradiction between the signals of the system on the control condition and the persistent exciting. So the new idea, we think about that. If the historic data can be used to achieve better model estimation, we will try the application of the digital twin technology. The digital twin system includes 2 entities. One, the physical entity, for example, in the graph, manufacturing, smart factory, smart car, farming, human health as a physical entity. And another part is a virtual entity. Is a computer-generated representation of the real system. For example, simulation, modeling, and optimization, data management, etc. We just have introduced two parts. One is about test equipment, just as the physical entity. And I have introduced the simulation platform just as a virtual entity. So we have the condition to do the research for digital twin system. There are two direct connections. First is from a physical entity connected to virtual connected. We can use a physical to virtual connection to optimize and updating virtual system. And the other connection is a virtual to physical connection. It important, very important. It closes the loop between hypotheses generated in the virtual and the real entity. So effectively, the digital twin with both connection hypothesis and subsequently perform test and adjust the hypothesis in the continuous adapting and improving cycle. Adapting and improving cycle in this figure is called training rate. So we can consider the two parts of the system as a whole system. This is just the difference between the digital twin system and the traditional simulation system. There's a continuous connection between the two entities. So one, we consider the whole system used for the controller design of a challenge work. I think the stability of the whole system and the robustness of the whole system and the performance. Okay, so in this idea, I want to use the historical data for estimate models, use the digital twin systems. I think the hiding control of the ship is the fundamental of the other tasks. Just for example, the trajectory control, following control, and collision avoidance control, and docking, all based on the cost control. So it's important to research for the adaptive hiding control. Okay. In this research, we consider 3 degrees of freedom model of the sync motion, U, V, and R. You can see that the controller can perform a different task. For example, in the 3-dimensional space, we can realize height keeping, height changing, docking, and the trajectory following. But for different tasks, the state point of the trajectory in different position, located in different position in the 3-dimensional space as a group, point group. So we can use a different group to estimate a different model for different tasks. In my opinion, the models for different control tasks is different. So we want to use historical data for model estimate for different tasks. Okay, it's very important. This is perhaps there are many models for different tasks in the 3-dimensional space. So we call this is a model grid. And in different tasks, the model is called a cell of the grid. So we can consist of a model decision tree for the adaptive control. This is the steps. The first step, we can get historical data series from the real system. And the real data series can be classified for some categories for different tasks. For example, for head keeping, head changing, following the trajectory, following control, etc. Some categories of data. And then we will remove invalid data and remain valid data to guarantee the data used have enough persistently exciting condition. Then we can use some identification algorithm to form the model decision tree. Okay. Finally, in training cycle, according to the information from the real system, the task just performing of the SIP controller can be judged automatically. So we can, according to the task just performing by the controller, we can use the model decision tree, suggest a more effective model for the controller to improve the performance of the real control system. There's the new idea for the effort. Okay, that's all about my report. Thank you.
Oh, yes, please. Thank you, Professor. Interesting presentation. We have interesting presentation. So any questions and comments from the audience? Please raise your hands. Let me know that. No. So, okay, so I have one question. Sorry, two questions for your presentation. Is that okay, Professor? Yeah, can you hear me?
Looking off.
Can I ask you that? Ask you a presentation? No?
Okay, okay.
Okay, so I have two questions. One is I would like to know more precise about the radar test equipment. So what kind of research did you carry out using the such equipment?
We just carry out a project of the smart ship mission project about the situation awareness. Include the equipment introduced just from that project. LIDAR,
Yeah.
direct camera.
So I think that you applied some AI or recognition algorithm to use to the radar system. I think that I want that. So I would like to ask about that. No, but your comment is no, and just only introduce your facilities. Is that correct?
We just use some deep learning algorithm for the classification of from the point cloud data from the LIDAR system.
Oh,
LIDAR system we can get LIDAR data many point cloud. We can use this point cloud, use some deep learning algorithm to realize the object detection and the classification.
Okay, I see. Thank you. So, and the question is about the repeatability of the control algorithm of the using the artificial AI or something. Final presentation, you use some neural network, similar kind of neural network was, I think that. So I worry about the repeatability of the control algorithm of that. you have some comment about it?
Yes. The performance of the algorithm, we are just testing. We can't give the more detailed result now.
Oh, okay. Thank you very much. So any other question or comments from the audience? No? Okay, a little bit early, but so we would like to move to the next presentation. So thank you very much for your presentation, Professor Liu. Thank you. So next presenter is Laurent Berry. Is that correct? Sorry, and my pronunciation is too bad for that. So, and from the Bureau Veritas from France. Yes, please start your presentation.
Good morning and good afternoon, everybody. I hope you hear me well. I will share my presentation.
Yes, we can see your presentation. Thank you.
Perfect. Thank you for having invited me to share our development. I am Laurent Vernet. I am at the head of the development department, which is in charge of the classification rules development. And of course, the development of these rules include the one which integrate the smart and autonomous navigation technology. To give you an overview of what we are developing, I will start with an introduction of the company, presenting then you the existing rules. The second important thing will be about cybersecurity, for which we have also some rules, and then I will elaborate a bit more on what is dedicated to smart chip and what is our next development. I will say more the current development, and like the other presenter, I will introduce how it relies on R&D project. So let's start with the introduction of Bureau Veritas, and more specifically Bureau Veritas Marine and Offshore, which is the classification society. And I have selected to give you an introduction what we are calling the tomorrow's challenge. In fact, this is the today challenge we are facing and we need to develop. There is, of course, the main topics, I would say, for the shipping currently, which is decarbonization. And in the parallel session, my colleague, Blandine Vicard, will give you a similar presentation about the rule development we are proposing for sustainability. Safety forever remains our core expertise, and we are continuing to addressing this in order to manage the challenges. Digitalization is we can say the decade challenges, and when we combine all this, when we want to have ships which are more greener with safety and integrated digitalization, we are facing the smart chip challenge. And I will present you today what we are proposing to have a progressive range of classification notation in order to acknowledge the performance of this new smart chip. Before moving to the rules, I would like to share with you what we remind from the discussion with our client and how we can summarize the objective of smart shipping. This is very consistent with what has been presented in the two first presentations. First, and I will echo again that in green, the ships are to be more sustainable. This means the reduction of the fuel consumption and the emission. All of this is to have a more efficient operation. You can improve the space, the carbon management, and other things on your ship. Safety remain one of the first objective, and we want to reduce possible damage, the crew exposure, and have more robust IT. And then when you are doing all this, you may expect to save some cost, which is a key topic as well. So let's start with the existing rules we have developed for autonomous shipping. It started in year 2017, the publication, and we have started 2 years before. At this time, the challenge was already to be more sustainable, efficient, focus on the safety, and in order to provide some cost. We want to have a very pragmatic and incremental approach. This is why we want to propose something adapted from remote control to partial or fully autonomous shipping. And of course, it will start from small ship first, and then it can be probably extended to larger ship. The challenge was to interpret and give some guidance with the existing, as an example, for the IMO guidance. And then we issued this guideline in December 2017 in order to be able to have some recommendation, some guideline for few projects. After that, the year after, in 2018, we received around, let's say, 140 comments. Some comments come from China, but it was very worldwide. It was from clients, from the equipment manufacturer, for the flags, and also from our internal command, from internal network, regarding the challenge that my colleague may face with the client. The year after, in 2019, we have digest all these comments and implemented in our rules, and now the rules have been updated in October 2019, and it's available on our website with the following links, and we will see all these consolidated rules. To give you a flavor of how it organized, our approach remains on the 3 main facts. We have first to perform a risk and technology assessment in order to qualify the new technology that are implemented on those smart ships, whatever the level they are, from simple monitoring to fully autonomous. The second focus is the functionality which are implemented, and it can be very different type from an autonomous ship to another one. And we have to check that the minimum level of functionality is appropriate. And finally, the third point is the reliability of all this. So with this guideline, you may find some recommendation regarding the design, the level of performance, and the quality assurance methodology to be settled. And if you see, our guideline is organized accordingly. There is a first section about general consideration of autonomous shipping, and then you have the 3 main concepts that they have introduced now. To give you a flavor of what we may found in this guideline, there is an example of the degree of automation that we have selected. It has been updated and is consistent with the IMO regulation guidelines. And you have 5 levels. It starts for the very conventional type of ship, and the ultimate level is the fully automation. And then there is three intermediate degree of automation. First, when the crew is supported and assist with some system. but the crew remain the authority. A second level where human must confirm what is proposed by the system. The third level is when the crew supervise what the system, only supervise, sorry, what the system proposed to them before the full autonomous level. So very generally, this is the framework of what we have developed. As I said, the second point, very important, was to propose some guidelines and rules about cybersecurity. The year after, in 2019, no, sorry, it was in December 2018, we issued for the first time some rules about cybersecurity. I will not go deeply in this rule, but more take the opportunity of this meeting to present you the full family of the notation and the services that we can propose to our client. You have in blue what is proposed by a subsidiary that we are calling Bureau Veritas Solution Marine Offshore, which is services to help you to achieve the level required for the cyber security issues. And then in red, you have the notation of services proposed by the classification society, as means the approval of the system or the concept that we are submitting. It starts for the very basic ISM compliance. Then you have all the family regarding cyber managed family in order to confirm that you have the relevant procedure. And then what is dedicated to the equipment. If I give you more details on what you can find, the first is, as I said, is the compliance with the International Safety Management Regulation. I mean the IMO code, in order to be ready for the risk assessment and the crew training on the ISM procedure. Then there is the preparation of the cyber managed notation proposed by Bureau Veritas. It means that to check that on board all the procedure that you have and the inventory, the risk assessment are duly prepared. When this is approved by the society, the cyber managed notation is granted further to the document review, all this procedure review and the test review, and there is of course annual survey in order to check that all this is properly maintained and remain in compliance years by years. After this first level, we can go deeper and propose extended services. It will be focused on the equipment in order to check that at the new building phase, the implementation of all the equipment that are necessary to have a smart chip are properly made, and you have the list of the support that can be proposed. And then if the design approval of this equipment and the survey is properly made, we can grant the ship with the cyber secure notation. And we also propose, after having do that for one ship, regarding the fleet management, we can also propose some services. Just to summarize what we are proposing for the cybersecurity, for the compliance point of view, to check the cybersecurity is properly enforced, there is, as I said, at the procedure level, the cyber managed notation. When we go to all the equipment on which the cybersecurity relies, there is first the type approval in order to rely on the appropriate equipment. And when all this is confirmed at the new building stage, you have the cyber secure additional class notation. And to prepare all this, we can also, with our subsidiary BV solution, propose you some assistance. It can be the ISM ready and the IMO compliance, but we have more sophisticated services now, and it is powered by Secura, which is a company that BV acquired at the beginning of this year in order to provide more support until the fleet, the management of the fleet regarding the cyber security point of view. That was the two first points in order to present you what is existing and what we are proposing for managing the autonomous shipping, and the very important prerequisite, this is the cyber security, and BV is very involved in that, and we are chair the cyber panel and the IX association. And now I will move what we are developing now for the smart ship. To present the framework, because we have to assess the smart function that may be available board on ship. In the two previous presentations, we see that all the tests and all can be related to navigation and so on. We decided to have an approach, again, something very incremental and progressive in order to acknowledge each level on the progression of the automation of a ship until the autonomous level. So we propose 4 tiers. The first one is about what we are calling a computer-based ship. This means that the first level of smartness of a ship, it's when you are implementing some sensor. Of course, you see some monitoring at the bridge level in order to have the relevant support for the navigation. It is also, you see some monitoring here on the ship regarding the machinery, and it can be also for the hull and all this. So the first tier for us is to have the proper data collection on board in order to monitor what's happened for the operation of your ship. The second tier will be how this data that you have collected are transferred to the shore. And of course, it means that your ship is connected with relevant cyber security requirements, and you are able to send that. After that, what we consider as the third tier is the communication in the opposite direction. It means that you are available to bring some support, but the support are not from the crew, but from the shore this time. And it's, let's say, what we are calling the remote support, or what can be called summarized, in augmented chip. And then, when this support, I mean the prediction and so on, can be directly provided by the system on board, this is for us when the ship becomes really autonomous. In order to rephrase all this, I will try to re-explain the 4 tiers in one single slide. So, as you see, to reach the autonomous level, you need to have real-time monitoring on system, be able to have some predictive, some automation on board, and of course, the relevant remote access. So to do that, first, you need computer-based chip for the collecting of the data. Then this data are transferred as your chip is confirmed to be a connected chip. So you have the arrow in green with the transfer of all the bytes to the shore. Then all this data are analyzed in order to make some prediction and bring some support from the shore, or no longer from the ship. This is the yellow arrow with some remote operation. And when all this can be on board, we are reaching what we are calling the autonomous ship, when everything is remotely on control on board. For that, now we have another rules, which is the 675, and I will present you what we are proposing in order to grant some ship with the notation that confirm the smart function. We have the last publication include the two first tier, one for the monitoring and the second for the connection, and how it is organized. To be granted with such a notation, you have to fulfill the requirement of the rules, and it's something that can be packaged according what is available on the ship. For example, for navigation, and in order to acknowledge that you have a relevance system, if you have all the requirements from our notation, IBS for integrated bridge system, and of course the INS, the integrated navigation system, then you receive this notation, and this notation is the requirement for the tier 1 of for navigation, for the system which have dynamic positioning, something equivalent can be accepted. And when the ship has meet all the requirements for the cyber managed notation, we can, in addition to the tier 1, we can propose it the tier 2 of navigation. This is very similar to what we are proposing for machinery. For machinery, we can the smartness can be for operation or maintenance, or for both. It can be when there is some integrated machinery system or some condition-based maintenance. For that, that can be a way to reach the first tier for the machinery. And then if you have also the cybersecurity requirement, you can reach the tier 2. And we have the same for the hull. When whatever you have some load instrument, this is the LI notation that you can see, or the monitoring of the hull. And of course, when there is some cybersecurity, it can be granted for the hull as well at tier 2. All this is available on our document 675 that is available on our website, according to the link you can find on this presentation. Finally, because you see that the tier 3 and the tier 4 are not yet published, all this will rely on the project you are currently delivered, or the research project in which we are involved. To give you some indication of what we can deliver on which the R&D project you are involved in, I would like to first present you what we did with Seoul about their concept they are calling ROS. ROS means Remote Operated Services at Sea. Again, there is a link of on our website in order to see the approval in principle that have been delivered this year to this ship dedicated to support at sea. We have completed the first phase with a proof of concept phase, and then we are starting a new one in which the French flag will be involved, because again, it's important to be in line with all these requirements, the statutory and what can be maybe proposed by the IMO. So this is an example of the real project, the development project that may exist for the tier 3, I mean for the remote operation. For the fourth level, the ultimate one, for the fully autonomous ship, it will start, of course, with smaller one. You have an example of another IEP that we propose for the DRIX concept developed by XBlue. There is a link if you want to see the video on YouTube, and also a link on to our website in order to see to have more detail on the approval of principle we deliver for this USV, I mean the human surface vessel, that will be the first type of autonomous ship that we will see, and this one is used for hydrodynamic survey. After these two examples of concept or demonstrator that exist, I mean commercial project, I would like to talk a bit about R&D. You have already been presented with the Novimar project, where BV was involved in the first presentation by the Wuhan University. I would like to propose you another one regarding a joint industry project, because as it has been mentioned, it's very important to have some real tests, and but of course it's very expensive, and we need to gather all one in order to support that and gain the experience from that. The first time we have been involved in such a joint industry project, it was for a Dutch one dedicated to autonomous shipping. There was 17 partners in this project, and BV was a partner as the classification partner and dedicated to the rules and regulation. For us, it was the first time that we have the possibility to get in contact with some sea trials that have been made in the North Sea in the Dutch sector. The ship was outfitted with collision avoidance system, and we see the autonomous ship is the one you are seeing in green. And it was very interesting in all the scenario and the testing made to see how this vessel interact with the real seagoing traffic. I mean the one you are seeing in red. For this GIP, if we try to put on the scale of the automation level that is providing in our guidance, we were at the level A3. It means that the system was controlling the ship navigation, but there were also still some human supervision, as you see on the picture. Finally, after Novimar, now we are on board another European project, which is in the H2020 project, which is called AutoShip. AutoShip is a project that will propose some demonstration with the full autonomous for the full autonomous ship. I mean, there will be smart, green, and ready to transport integration. The ultimate focus is to have some demonstration with TRL, I mean a technology readiness level at the minimum of 7, regarding autonomous vessel, and there will be two sea trial, one regarding inland navigation and one in the open sea. For this project, which will run over 42 months, BV will be involved on the leader in the packages dedicated to regulation, analysis and rules and cybersecurity. And these packages are almost finished, and now we will enter next year in the demonstration phase in order to see how all this run. And to conclude, I will summarize all that I have presented today. So, as I said, we have a very pragmatic and very incremental approach in order to start with the two first tiers that are already available in our rules. And it's important, and I thank you again to have invited me to share, because we need to share, to rely on the partnership on industry projects which are developed. That will be very important for us for the tier 3. And of course, all this AIP, this USV, and our participation in the IMO group for the regulation will be important as well to consolidate the final level. And then I thank you for your attention. I am available if you have some questions.
Yes, thank you very much for your presentation and give us a lot of interesting and useful information. So anyway, any questions, comments from the audience? Please raise your hand or turn on your mic.
我要问一个问题。
Yes,
Well, I have a question.
Yes.
Question.
Yes, please.
你好，这个
Hello. Mr. Laurent, I am from Harbin Engineering University. My name is Xia Guihua. Thank you very much for your amazing presentation. I have two questions. The first question regarding autonomous intelligent ships in France, you have shared with us a lot of examples. And can you further explain the degree of development or the extent of development, and then which universities in France are doing research in this regard?
I don't receive the translation. If you can help me.
The first question is, to what extent has France been carrying out research in the regard of intelligent autonomous ship? Can you hear the interpreter? Can you hear the interpreter, sir? Mr. Verney, can you hear the interpreter?
So, and you can select the translator.
The interpretation, yes.
Maybe and talk again about that. You can select the translator.
Can you hear the interpreter? Testing, testing.
So I didn't catch what was the question.
Can you hear me now, sir?
Or send me later on. I will answer when I receive it in English.
Sorry, we cannot hear
Testing,
that.
testing, interpretation, testing. Can you hear me?
Okay, I see now. If the question is that if there are French university involved in maths, I will say no for the example. For the full autonomous shipping, it's more for industrial partnership, but the university are more dedicated or specific component or specific thing. They are involved in project, but they are not either in the full mass project.
Okay. So is that okay, Jose?
I hope that I fully catch the meaning of this question and my answer is appropriate. But feel free to send me an email. I will do my pleasure to answer you.
Yes, yes, please. So that because then so already time has come, so we need to move the next speaker. So thank you very much for your interesting presentation again, and impressive for me that. So keep in touch. Yeah. Please send the email to him that to any question or comment to that. Thank you very much. So next, I would like to ask my presentation, Professor Hans-Peter Hilde, and from the Norwegian University of Technology. Please start.
Thank you very much. Thank you very much, Professor Etsuro Shimizu. And ladies and gentlemen, Wuhan University, I guess you can hear me.
Yes, I can hear you. That I think can hear.
Thank you. I will first present some examples of autonomous shipping in Norway and some projects, and then I will be into how we can maintain distributed maritime capabilities, what is going to happen on board and what is going to happen in shore centers. First, a major research program in Norway is called SFI Autoship. The major players in Norway in autonomous shipping is a part of this project. You can look it up on Google. A key element in this project is the business models, use cases of autonomous shipping. I will be back to some of them later on. Project involves autonomous shipping and all handling of all these complex environments, communication, and as well as remote centers and remote control centers into this. The use cases is 4 use cases. It is deep sea shipping, bulk shipping, and then short sea container shipping, urban ferries, and offshore support operations. And simultaneously, we are also building a lot of infrastructures at universities and research centers to deal with this type of challenges. Here is just a few pictures from SINTEF, from NTNU, and so on. This is one of the examples, Yara Birken. It is a container vessel. I can show you a video. This container vessel will replace trucks. That is transportation between 2 harbors like this. And it is autonomous ship that will replace this huge traffic between these 2 points. And the ship is designed, equipped, and it will be up running from next year. It is 100% electric. It will be without any manning. It will be manned in 2022, but later on it will be without any people on board. And even the harbor operations and everything will be automatic. This is a kind of significant research project put into practice between these harbors actually. And you can see it is a set, it's fully automatic between these harbor things and so on. With collision avoidance and all these sensor systems and so on is introduced. This video is also on the net if you want to go deep into what they are doing and so on. The control center for this ship is also built. It is also the chief engineer and also the nautical people will be sitting in control centers, following the traffic and following whatever that is happening.
Oh, excuse me, Professor. So we received a comment from the audience. So may I ask you to make your slide more bigger? Because the display is too small.
I don't know how to do that. It is on my full screen.
Oh, okay. Oh,
On
sorry.
my slide, it is a full screen.
Maybe white, you use a white screen so that black part is almost half part is a black. If possible, that.
Boy. I'm not quite sure how I can do it.
Okay, maybe use the right button and maybe changing the size of the screen or something. No.
This is usually working, so I don't know how we can fix.
Okay, so yeah. Okay, so we have time is limited, so please start again about that. So sorry for the audience.
Then I have to start sharing again, I guess.
Yes, please.
I'm sorry for that. It looks good on my screen, so I don't know how to fix this one.
Okay, sorry, and so I don't know about that. Sorry. Yeah, yes, please continue your presentation. Thank you.
This is another example from DNV. This is also a kind of revolutionary design, unmanned, zero emission, short sea vessel. This is a 60-meter long ship that is in the research. Then it is quite many research projects ongoing, making these smaller USV ships that is in testing in the fjords around Norway. It is quite many projects like this, testing, verification, functionality of autonomous ships. I think it is 5-6 projects like this in Norway at the time. This is a project called CBUS. It is a zero-emission autonomous urban mobility. The idea is that it is quite expensive in bigger cities in the harbors, and how we can make urban mobility in this. And this is also built when it is tested in Trondheim. So it is a ship that is moving back and forth, as you could see on this place. And it is equipped and it is up running in Trondheim harbor at the time. So I think it is very important to do this type of testing and verification. As you know, these IMO definitions of autonomy, 4 levels, and the 2 first level, it is pretty much the people are on board. And the 2 next levels, as you know, the people are not on board. Now we have been working, first of all, about digging more into these 2 first levels. And it can be a discussion of these levels, if you have an axis of time, an axis of number of ships, I don't put exactly time frame of this, but of course, I think it is quite obviously that the most development in number of ships will be in level 1 and 2. Level 2 is remotely controlled ships, but with seafarers on board. First of all, people on board taking care of the engine systems and so on. And what type of level, number of ships it will be that is fully autonomous without any people on board, at least in the short term, will be fewer ships. So now we have been putting a lot of effort into these two first levels. And we call this how we can get distributed maritime capabilities. What is the crew doing on board and what is the crew doing in ships or shore centers? We call this how we can make these type of dispersed teams that is partly on board and partly on control centers. And in generations, ship systems have been quite isolated, and the culture on board is to handle quite isolated actually. And it's not only about technology, it is about humans, it is about the crew and how to deal with ship systems like this. And of course, how we can make these distributed capabilities between shore centers. The drivers for this is, of course, increased connectivity and more and more Internet of Things type of solution. It is growing by factor 5, 6 within few years and so on. So I think this future of the new type of ships will be, we will see it quite fast. Then, how to link sea and land closer together? What type of seamanship can be merged between sea and land? It is how can we make this strong team operating the ships? We have been then looking into use of digital twins. We can instrument the ship, send all information to the shore center, and by use of digital twin in the shore center, be able to do simulations, verifications, and so on, and communicate back to the onboard crew or give direct commands to the ship from the control centers. I think the digital twin is the key to achieve this type of close connection. So we have also been building this type of centers using the Gunerus, that is the university's research vessel, all instrumental vessels, and we are building this type of shore center based on a digital twin technology. And there's a lot of elements in the analytics, but also visualization, teams, understanding of the operation, and how we can transfer what is the real situation on board a ship and transfer this to the control center and get joint seamanship. And in the next phase, it is also about how we can add suppliers, customers, harbor authorities to the same system. Then, few examples of what we are doing. This is more offshore operations and what we can achieve by using digital twins. Of course, we can switch on and off the sea. We are not transferring only pictures or video screens from the ships, but we are sending this to a digital twin and we are reshaping the situation so we can switch on off the sea, so we can see the seabed and see the situation in another way than the crew on board. And of course, we can do simulation of the situation. We can ask the ship to be standby, and we can do simulation of the marine operation. We can even do the lifting operation in the simulator just before the ship are doing this. So we can test operation in different weather conditions and so on and so on. So we are doing this in the center. And of course, we can use, when you have a digital twin, we can also do briefing of the crew, virtual crew that is partly on board and partly in land. We can do briefing of operation that is going to take place. In and out and discuss over distance the work tasks to be performed. A little bit late, so I think I will skip some of this. And of course, when you have a digital twin, it is possible to do projection. And we can calculate the response to the system in hours in front of you based on weather changes and weather forecast and so on. I think digital twin is a key to achieve this close cooperation between the crew on board, the office in the control center. And of course, the technology will also be on board, and the same technology will be in the control center. So they can look at the same simulation and so on and so on. And of course, during the operation, you can do a lot of simulations about what is. Then finally, I can show you a link, a video screen of our ship Gunnerus. And this is from our shore center. And we are using students and employees dealing with the shore center. This is from the navigation screen. And this is shore center. You can see that there is Gunnerus. We can choose if you are looking from the situation out the window from the ship, or whatever angle you want to study the operation and follow the ship actually. It is only the position, velocity, heading, and so on that we are transferring to this center, and we are reshaping the situation. Also, other ships will enter into the scene based on AI's data from ships in the surrounding. And of course, we can also, the crane and equipment is a part of the digital twin, not only the ship. And we can run, you can see, we can run the crane left. It is only representation. We are only sending the joint angles of and all the equipment. Then we are making this virtual scene to the left. To the right, it is the video screen, but then you need much more bandwidth to send it to the shore center. So by this, we are proving that just by sending the joint angles and such situation, you are able to rebuild the virtual part of this. I'll jump a little bit. And of course, then we can establish different digital twins. To the left, the movement of the ship is exactly as measured on board the ship.
Давненько не ездил. А что там? Это у тебя конференция, нет? Да. Так,
Пометьте от себя. Sorry, Professor, disturbing your presentation.
And then we can have several twins. We have one twin that is moving exactly as the ship in the real life. And we have a green one that is moving according to by simulated movement. By this, we can actually also test and verification in another sea state than the real digital twin, or the real ship, I'm sorry. So actually we can do several testing and several verification, and also we can then put on another sea state so we can test critical operations in another sea state if we like. Like you can see here is another sea state. You can see the light blue digital twin is moving according to this sea state, but in real, the ship was not moving that much because the sea was falling. I think we are running late, so I think we can just go to the conclusion. I have shown that it is many autonomous shipping projects in Norway. And we have been now in my group, first of all, digging into how we can maintain distributed maritime capabilities, how we can merge teams on board with teams in control shore centers. And we have been digging into how digital twins can be a tool for the people on board, but also the crew in shore centers to do verification, simulation of the situations, and doing a lot of simulation, risk simulation for collision, for operations, and so on. Thank you very much.
Yeah. Thank you, Professor Hilde. So, and very interesting presentation and introducing us the many projects carried out in Norway. So, any question, comments from the audience? Please.
我有一个问题。
I have a question.
So, Professor, can you
hello,
hear the
Professor.
English?
I can hear you.
Oh, yeah. Please.
Thank you. Professor, are you listening to the interpreter? Well, I have two questions for you. First is the digital twin you just showed us. Have you achieved the real-time interaction between physical ships and the digital twins? And then, in terms of performance, what is the difference between the digital twin and the physical ship?
Yeah, we did some testing with this research vessel about this type of dispersed teams now 1 month ago. Our students was crew on board the ship, and we have other students in our control centers. And it works very well, actually. And so we are quite happy with the results, but this is something we have to dig much more detail into. We have some challenges with the technology and all these things, of course, but I think this is a quite promising approach. The benefit of a digital twin, I can explain that. In previous attempts, and also a lot of research are showing that if you don't have these simulation capabilities, the people on board are using all their effort, sending information and knowledge to the people in the control centers. They are spending most of the time informing the people in the control centers. Then you will not have a good team. By this, the idea is to build up as rich information in the control center as possible, and make them able to run scenarios, simulations. So actually in the control center is giving information and knowledge and understanding to the crew on board. We have to change the loop of information. And then you need a digital twin. So you can do a lot of scenarios and simulation and verification by this tool. That is the idea. So that is why we are not only sending and building up exactly the same information on board, like video screens, we are building up simulation models that can be used for verification scenarios and so on. Thank you.
Thank you very much, Dr. for that. So could you see that? And the professor, could you see the chat? So we have two questions from the audience. That one is, may I could conclude that it may take a long time for ocean transportation to be completely unmanned. However, your unmanned ship technology may be the first to realize coastal transportation and inland river transportation. Maybe you can see the chat. So is that correct for that? From the
Now I can see the chat, yes.
Yes, yes, please.
No, I don't think accuracy is the main challenge, and not communication or delay actually, because by this framework, we are sending very lean information actually. Position, velocity, and such things is getting in a high rate. And other information much slower. So this is quite fast actually. It is very fast, and we are rebuilding this information in the simulator. So I'm not very worried. I think the key is to have in the remote centers very good simulation tools and also application that they can run collision avoidance. We can make heat maps of risks and all these things, how to make these computerized tools in the remote center. I think that is something that is the most challenging to develop. I don't think communication accuracy is by using this technology I think we have solved that by using digital twin.
Thank you very much for your answers. So any questions or comments from the audience? No? Yeah, okay, thank you very much. Oh, sorry. Sorry, and one question from the audience. So we received the chat. So I would like to, you can see that?
Yeah, I can see it, maneuvering models.
Yeah.
Maneuvering models is a challenge. I did not get into this topic now. Our approach to that is we are starting by the best numerical models that we have. On top of that, we are using machine learning to improve those models. It is a little bit two worlds. Somebody believes very much in the numerics and the physics, and some is in machine learning and this type. And we are merging this actually. So we are starting by the best numerical models and then adding machine learning on top of that. And of course, for berthing and these accurate situations and shallowing effects and so on, it is challenges. The project I showed you, like Yara Birkeland, it is a ship that is transferring, going only between two ports. So you can learn by getting into this port. The challenge is, I'm not quite sure that this learning is valid for other ports and other situations, but you can learn quite fast by predefined ports. And also, you can also add more instrumentation in this port, in the when you are doing this learning, you can add ADCP that is doing measurement of the current and waves in this very narrow effect and so on. But this is a very important area for research actually.
Yeah, thank you very much for your answer there. So almost time has come. So thank you again for your presentation. Thank you, Professor. So anyway, so we would like to take a coffee break and 10 minutes coffee break. So next session, we would like to start the 8 in Greenwich Mean Time. So we'll take a 10 minutes, almost 10 minutes break. See you later. And so I have one question to the Wuhan University of Technology person. So could you tell me the name and the professor or some others, and who will be the co-chair of this session? Sorry, I have not received any information about that.
Yeah, sorry for that. The next chair will be the Professor Wen from the Wuhan University of Technology.
Yeah, okay.
And I think he will be here in 5 minutes. Yeah.
Yeah, okay, thank you.
Located in Wuhan, central China, with 60 years of history, Wuhan University of Technology is one of the to meet the needs of the fundamental components of Wuhan. Event 2000. And the spirit of sound and morality, broad in learning and pursuing excellence. The university focuses on the lofty ideal of building an excellent university to win a worldwide recognition and admiration. Adhering to the strategy of strengthening itself through talents, WUT boasts a large talent group. The number of academicians has increased from 0 to 11. Among them, 5 are members of Chinese Academy of Sciences and Chinese Academy of Engineering, and 7 are academicians from developed countries. A high-end talent team composed of specially invited experts and chief professors has been built. Adhering to the concept of technological innovation, efforts have been made to carry out original innovation and make breakthroughs in the core technology research. A large number of high-level scientific and technological achievements with originality and social influence have been yielded. A series of original results obtained in the cutting-edge science field from the intersection of material science and energy and life sciences have been published in the world's top academic journals and have been cited by more than 115,000 scientific researchers worldwide. More than 50 research groups in developed countries have followed up and studied these researches. In 2018, as national statistics showed, WUT ranked 17th in the total number of 3 national awards for scientific and technological achievements among all Chinese universities. WUT focuses on transferring scientific and technological achievements into social productivity. It has made great contributions in serving major projects. The transformation and upgrading of the 3 major industrial sectors, and the development of regional economy and society. A number of important innovations have been achieved in green building materials, new energy materials, electronic information materials, biological materials, and new marine materials. Major breakthroughs have been made in key technologies for the large-scale use of solid waste and domestic waste as alternative raw materials to produce high-performance cement. These advancements have promoted the transformation and upgrading of China's cement industry. Achievements in key technologies have been widely used in more than 150 major national projects such as large-span bridges, tunnels, high-speed rail, highways, and the Three Gorges Dam, etc., and made significant contributions to the development of China's building materials industry. In the preparation theory and technology of fiber grading sensing and smart sensing, industrial production and engineering applications, WUT has solved international technical problems and formed a complete intellectual property system. Scientific and technological achievements have been applied to major basic engineering and equipment fields such as chemical industry, metallurgy, railways, highways, ships, ports on a large scale. A number of important innovations have been achieved in the fields of green smart ships, water and land transportation safety, smart transportation, and smart shipping, etc. WUT proposed and established the navigation brain system of intelligent ship to promote China's ship-driving active safety technology and equipment innovation. The design and construction of the first direct river-to-sea demonstration ship, Han Hai No. 1, has opened the 1,000 boxes era of the Yangtze River inland shipping. In the areas of automobile lightweight, electrification, intelligence, and networking, WUT has broken through a series of core technologies and promoted the transformation and upgrading of the automobile industry. One of China's first 2 fuel cell cars.
Hello?
Yeah. Yeah, we can. Yes, please start.
Okay, thank you, Professor.
Yeah. The same to you.
Just a presentation. Okay, ladies and gentlemen, welcome back to our invited speaker section again. I'm Yan Chaowen, the professor and from Wuhan University of Technology. It's my great honor to be the chairman of this section. It is with great pleasure that I welcome the first speaker, Mr. Rohit Sawada. Mr. Rohit Sawada is a researcher from National Maritime Research Institute of Japan. His research interests are in autonomous vessels and technologies to automate the ship operations. Let's welcome to his speech on introduction of research on autonomous ships in NMRI. Okay, Professor.
Okay, thank you for introducing me, Chairman. I am just a researcher, not a professor. My name is Rohit Sawada from National Maritime Research Institute in Japan. I'm a member of Autonomous Ship Project Team in NMRI. Today's presentation's title is Introduction to Research on Autonomous Ships in NMRI. Today's contains 3 first collision avoidance, and second pathing control, and the last is sensoring for autonomous navigation. Okay. Development of automatic collision avoidance for multiple target ships is one of the important tasks to realize autonomous ships. Many kinds of approaches have been proposed. However, most of existing approaches take account of only one target ship at once and are not applicable to encounters of multiple target ships, as reported by Veras in 2017. I don't explain about the core legs in detail, but we know about the core leg. The core legs includes only for rules only for 2 ship encounters, such as head-on, crossing, and overtaking scenario. So it is difficult to build a rule-based system based on core legs to multiple target ships. However, human pilots decide how to avoid collision flexibly based on core legs. So we have some approaches to reproduce the action of pilots. So we have taken approaches of combination of OZT for representation of danger of collision and deep reinforcement learning as a decision maker in this research. I want to explain about the OZT. It is obstacle zone by target. It is used for the evaluation of collision risk. OZT is an area, as shown in this figure, where collisions may happen in the future based on the dynamic information of ships. There is on-ship and there is target ships. So the areas where collisions may happen in the future will be shown like this. It is OZT, but OZT is an area information, so it is difficult to be dealt with using the deep reinforcement learning or other applications. So we have to convert the information of the T to the some useful formation like vector information. So we developed the grid sensor. Grid sensor is a virtual sensor to transform the this information to the vector form information. Grid sensor detects OZTs based on whether each grid set overlaps on them or not, and overlapped grid set represent the one value, and or not. If not, the grid set represent 0. So we present the where OZT as a vector with 1 and 0 values. Sorry. And next, I want to explain about the reinforcement learning. Reinforcement learning is a method of machine learning, and we use the deep reinforcement learning. It is a combination of deep neural networks and the reinforcement learning. Deep neural networks is used to represent value function or the policy. It is a brain of the trained model of deep reinforcement learning. The left figure shows the learning flow of deep reinforcement learning. There are two factors. One is environment and one is agent. Agent corresponding to the ownership, and the environment includes the target shapes and the waypoint or grid sensor and other information. And the environment makes state vectors and provides this to the agent ownership. The ownership decide the next action based on the state vector and calculate with using the policy function. And also, agent improve the policy function using value function and reward provided by environment. The aims of the learning method is the aims of the trained model is collision avoidance of multiple target shifts, as I said previous slide, and waypoint navigation also in parallel. We have to build a trained model that not only avoids collisions, but also considers the course to the waypoint. We use test scenario as shown in the slide. This is called the Ais problem. The Ais problem has 22 encounter scenarios shown in this figure. And in this scenario, target shapes don't change the course or speed in simulation. So collisions of target shapes except the own shape were neglected. And this is a network of deep reinforcement learning. And I don't explain about this network structure in detail in this slide, but these are the input grid sensors information. It means collision risks presented by OZT, and other information such as ownership's position, course, speed, and waypoint information. The grid sensor information processed through the convolutional network, and other information processed through the full connected neural network. And combine these results, the network outputs a radar angle. In this case, this network outputs discrete values of radar angle -20, 0, and 20 degrees. And I also skip the explanation about the design of rewards in this presentation. So someone have interested in this approach, please check my paper. Okay. So I want to show you some demonstration of the trained model. In this case, this is case 22 of EMAS program, and there are 3 target ships in this simulation scenario, and here is our ship. All ships should avoid these target ships and arrive at the waypoint. In this video, all ships go to the at the north, and the view is fixed to the head up. Ship turn right to avoid these target ships and go to the waypoint in this scenario. The terrain model by proposed method can approach a waypoint in this complicated scenario. The right figure is the trajectory of the simulation, and the left figure shows the minimum passing distance in the simulation. The minimum passing distance is about 0.36 nautical mile. It is about 667 meters, and the safe passing distance to complete the OZT was 0.3, so it is successfully works. It works successfully. Okay. Then we improve the model using other network structures and new calculation method of OZT. I also skip the explanation of the method in detail, but we test improved model in the more complicated scenario shown in this figure. There are 5 target ships, and this is these are the OZT. Let's skip. The result of the simulation is shown in the red figure. The red one is the trajectory ownership with maneuvered by the terrain model. The ownership can avoid waypoint target ships 3 and arrive at waypoint. That's all about the collision avoidance research in MRI. It is done in simulation. For the bathing control, we use the experimental ship to develop automatic collision, automatic bathing control. The experimental ship Simple was built in 2014 and utilized studies on seamless ship system for CO2 for remote islands and the lithium battery fuel cell ship experiment, etc. in MRI. From 2019, we use this ship for research of automatic bathing. First, we developed a mathematical model of ship motion to simulate bathing maneuver. We use this MMZ model based on the MMZ model as shown equation 1. The comparison of simulation result and experimental result of ship motion is shown in the right figure, and the top shows the trajectory of simulation and experiment results. Then the speed components, surge velocity, sway velocity, and the rate of turn shown in the bottom of the figure. This model fit to the experimental result shown in this figure. So we use this model to develop the automatic bathing control. Then the automatic bathing algorithm of automatic bathing control consists of path planning and path following. The path planning's function uses a basic curve to represent the approaching path to the bath, and the path following algorithm uses heading controller known as autopilot and the pure pursuit algorithm to follow the path. The function of the pure pursuit path following is shown in this figure, and here is a ship, and the red one represents the path to be followed. Ship follow path by following the target point, virtual target point on the path using a heading controller. It is a paper sheet and heading controller path-following algorithm. And the right figure shows the control sequences for automatic pathing control. Here is start point, and here is a birthing point. And we divide the path to the 4 section, and we switch the control mode of automatic pathing control. Then we approach to the path. First is a fast forwarding mode, and second is neutral mode, and the third is turning mode, and last stopping mode. Then we also developing monitoring and control user interface for automatic pathing control. This shows the trajectory of shapes and the other values. This is explanation of the user interface, and here is here's a propulsion panel. It shows a clutch condition, propulsion revolution, telegraph, and so on, and rate of turn panel, radar angle panel, and other data also shown in this panel. And the wind condition is shown in visual. And in the center of UI, we prepare the 3D plot area and the 3D map and the map CZ and the ship CZ and the target ship, target of Earth CZ shown as a yellow mesh polygon and path lines. Using this UI, we monitoring the state of the automatic pathing control and stop and run of control. Okay, I want to show some demo. This is about the experimental ship, and here is a pathing point, and the ship starts from here, and this green line is a path. The wind average wind speed almost 5 to 6 meters per second. For safety, ship approach slowly to the bus in this experiment. That's all for the automatic pathing experiments. I show some examples of experimental results of automatic pathing control, and this data is different from the previous experiment in previous video, but as shown in left side, our proposed method can follow the visual path precisely, and the right figure shows the sensor data of experiment, distance to the bus, surge velocity, sway velocity, rate of turn, and to wind speed, heading angle, and engine rotation speed, and propeller rotation speed, and rudder angle. Okay, that's all for automatic pathing control. At last, I want to show you some application of sensor in autonomous navigation. First, I introduce you our control system of experimental ship simple before explanation of the sensors in this ship. We developed the onboard control system consists of programmable logic controllers. Here is a user interface of PLC's control system. It is basic control system UI, and this is version support your user interface. And PLC has also has other user interface such as automatic pathing and waypoint control, remote control. The architecture of onboard control system is shown in the right diagram, and here's PLC, and the PLC connect to the actuator on the ship, thruster, engine drive unit, and the steering system unit. Also, sensors connect to the PLC, and the sensors data are collected to the PLC and send to the P laptop. It is calculating the path running or something in the system. So we use this many sensors for the automatic control. GPS and QZSS, it is so-called Japanese GPS are used for the automatic control, and QZSS for localization and GPS for heading angle. We are also testing LiDAR sensor for accurate localization near the bus. We use this real-time sensor, and we measure point cloud data in the experiment. This is LiDAR test in experiment. A right video is onboard camera captured by GoPro, and left figure shows LiDAR sensor data using Septum Vista P90. This is bars, and are showing this here. This case shows application of point cloud data from LiDAR to path planning. Right figure shows this application, and the dot points show the point cloud of obtained from using LiDAR, and this is a start point of ship, and this is pathing point. Using path planning with a point cloud from LiDAR sensor, we can generate paths as shown in this figure with blue straight line and the red straight line. Blue one is a backward path, and the red one is a forward path. Okay, I introduce research topics related to autonomous ships. The main points of this presentation are as follows. First, collision avoidance algorithm using deep reinforcement learning was developed and demonstrated simulation of collision avoidance in scenarios with up to 5 target ships. And automatic pathing control based on path planning and path following was developed and verified using the experimental ship. We also use many sensors to control and monitor the ship state during the autonomous navigation. QZSS, GPS, and LiDAR, etc., play important role in autonomous shipping. That's all. Thank you. I can't hear you.
Do you have any questions? Okay. Okay, shoot. Okay. The first on the board on board there are two questions. Two questions. Can you see it? The first one is how does the OZT handle the ship that might change its speed and course in the future? And the second question is what if the ship is navigating in confined water? Should the system still work?
So sorry, I can't hear you. Please say again.
Sorry, Mr. Sawada. So please check that chat on Zoom.
Yes. Oh, okay. Yes. Sorry. For first question. Okay. It is difficult for a problem. We think some probabilistic or statistical method to dealing with the change of the target ship's speed and course in the future. We are planning to Kalman filter to approximate the effect of change or of speed and course of target ships. For the second question, okay, this is also a difficult question. And in this research, we don't consider about the sensor to get the information about the target ships or some other obstacles such as the buoy or the quay or something. So it is a problem of censoring. So I'm working hard to solve this problem. But algorithm is will be work if we get the information of target ship or the other information to judge collision avoidance or the automatic passing. So that's all.
Okay. Any questions? Okay, thank you again, Mr. Sawada.
No, I have a question.
Okay, please.
I have a question. Professor Sawada, I see the result of the birthing is very good, but the bow thruster, if the bow thruster is irreplaceable, and if it's very important for your birthing control. Thank you.
Yes, this ship keeps bow thruster, but the problem of electricity, we don't use bow thruster in this experiment, but by using this algorithm, we can approach to the bus with only rudder and propeller control. So if other more difficult ship or bigger ship, we have to use a bow thruster for the busing.
I want to know if the side thruster, in other words, the bow thruster is very important in your control system.
I think important, but I don't. Yes, that's right. The side thrust, the function of side thruster and the bow thruster is same in the bow thruster to control your rate and your angle. So it is can be done by using a PLC controller or some algorithms, I think.
Clear? Okay. For the time limitation, let's thanks Mr. Royal Sawada again. Thank you. And now I will turn the podium over to Vice Rector, then to student Nikkei. Vice Rector student Nikkei is research from Admiral Yoshikawa Marine State University. His research direction include the mathematical model of fuzzy logic, stoical approaches to accessing the reliability of navigation information, neural networks in marine mobile object motion control. Please welcome Vice Rector Julian. Please, Vice Rector.
Just one moment, I'm launching my presentation now. Are you able to see it now? Or can you confirm it?
Yes, yes.
Okay, I'll try to put it on full screen. Yeah. Okay, so today I'm presenting the report on the topic of the issues of the autonomous shipping. It's a little bit different from which was in the program, but I think it's close enough. Okay. First to our concept. The concept of autonomous navigation developed in the State Maritime University after, our State Maritime University named after Fyodor Fyodorovich Ushakov, consists on the basics of the so-called Mayak or Lighthouse project, a technological development of autonomous navigation in Russian Federation. The project involves the technical implementation of comprehensive infrastructure solution for management of autonomous vessels in the seaports, including technical solutions for vessels, coastals, and sea segments. The concept, as I already mentioned, has main parts which are presented on the slide, and namely, a system of high precision navigation for large tonnage vessels, that means the vessel segments, mooring operations monitoring system, and that's a coastal segment, automatic hydrometeorological monitoring system, and that's a sea segment, a communication system combining those three segments.
问他一下，咱那个 PPT 不动啊。
It seems that your slide is not going. Your slide is not going right now.
The sound is coming very badly, but you cannot see my presentation if I get it correctly. Or is it so?
Dmitry, and can you push the F5 for starting the presentation?
Well, why? I already did that.
Not yet, because we show only different slides on the left side, and that's all.
Okay, I'll try to restart it.
Okay, thanks.
So how's this?
And can you push on the F5?
I already did that.
Yeah, but okay, and you can.
It's perfect for my screen. I don't know. I'll try to restart the presentation. I'll try to restart the presentation from Zoom.
You can close and open maybe again. And...
Yeah. One moment, please.
Okay, and do you see in right side on down right side? It's like a list. Can you open like presentation? It's small icon in right side on and down. Right side down. It's like a presentation you can put if you don't want to use the F5.
I already did that. Can you see my presentation? Not?
Of course we see it, but it's not comfortable because it's too small, you know.
Well, I pushed F5.
I am sorry. Can I interrupt, please? This is Janne from South Dakota University of Applied Sciences. Could it be possible, because I've faced similar issues a few times, maybe this is implicit information, but could it be the case that you are trying, sir, to share a screen when you want to share the presentation, or vice versa? So if you have multiple screens, it's better to share the screen and not to share basically the application of the presentation.
Okay, I'll try to share the screen now.
Please try that, sir, because then if you have the slideshow available in one of the screens, that should work.
How's that now?
Oh, that's good. Now it's good. Yeah.
Oh, thank you kindly for your very time.
No problem. I will not charge anything for the IT support.
Oh, thank you kindly. Well, I'll resume now. If you can see, those are the three segments, and namely the system of high precision movement, and the mooring operations monitoring, automatic hydrometeorological monitoring system, communication system, which combines those three segments, and digital services for various needs that are not very close to the goals of those three above mentioned segments. The concept represents the solution of the main tasks of navigation from our point of view, namely identification of the state vector, which was actually mentioned many times before this report, route planning, of course, collision avoidance, interacting with modern port facilities and systems, as well as remote control of operations and communications based on the main segments of infrastructure changes. Ships, so-called vessel, coastal, and the shore segments. Yeah, you can see them represented in the slide. Now to the elements of the state vector we are mostly concerned of. We divided them in the three parts. That is the position part, of course, because of documents and IMO papers are referring to the position accuracy and so on. And this motion part, that is the speed vector, course, angular velocity, etc., etc., etc. Because it was very important not only to know your position, but also to know how you are doing in this position. And the last but not least is the weather conditions and their impact on the movement of the vessel. Each of these, okay, I'll just shift to the next slide. The task of planning a route is often considered an already solved task. Namely, there are various solutions offered on the market, but I'd like to highlight some instances. It is very important to have the planning from point A to point B. Usually this is referred to as berth to berth in the classical navigation. But however, there are many situations in which it is very important to plan deviation route, so-called deviation route. And that is the case where from point to point planning is applied. Then there's things you are that it is essential to implement as assessing the cartographic information and including the navigation support information. If you do not do this, the planning may be very, very dangerous and inconsistent with the task given. And the third part is so-called navigator's experience. And that is namely taking into account various features of navigation situation, which was experienced long ago. That is dangerous currents, dangerous congestions, anticipated congestions of trips, different aspects of the cartography, and so on and so forth. So the passage planning is not that easy. One of the main aspects which is not mentioned in the slide is also the safety aspect. There are many approaches to assess the safety of the route. But however, it may be now a difficult decision that is referred to navigator's choice, actually, if it is safe or not. Well, now to the next slide. As for the influence of the weather, there is a expansion of the system for calculating the impact of hydrometeorological factors on the vessel developed in our university, including the forecast of the impact on the planned trajectory in the future. The display can be presented both in the classical navigational style and in the style of displaying various elements of the influence: wave, wind, current, and as well as their combined influence. There is an option to calculate the influence for target vessels as well, and that is very good. As you can see, the presentation shows that there is a possibility to highlight the element's influence on the vessel. If there is a system developing the impact of the waves on the maneuverability on the ship, but that is just in the development also. For some data. To provide the navigator with the reliable data, the concept of the weather conditions fields is provided. To do this, the water area is divided into cells of certain size, quite a small size, I might add. And hydrometeorological data is applied. This allows us to switch to using the extrapolation algorithm, which greatly increases the integrity of measurements and the integrity of this whole system. Well, the results of the work from 2016 to 2020, tests of technical means of high precision vessel movement and mooring systems based on the satellite and inertial navigation systems, including which were included in the ship segment, were carried out in the port of Novorossiysk. In 2019 and 2020, tests of joint work of ship, coastal, and marine complexes or segments were carried out, and they were carried out successfully. The slide shows the registration rights to some ideas of identification of state vector and the pathfinding segments. Additionally, there are certificates for the equipment of all three segments presented in this concept. And now I'll try to demonstrate some video. Maybe that deepens the results. The video is going on. You can see it, yeah? Can you confirm? Can somebody confirm?
Yeah, we can see that.
Oh, thank you. Mm-hmm. And that is that. Okay, I'll try to speed up a little bit because we lost some time. Now, the second part which we want to elaborate about is the decision-making systems. First of all, we cannot speak about autonomous vessels in any way if we are not mentioning the collision avoidance systems. As for the previous speaker, we share most of the info given, but however, there's a scope of the problems presented in that slide. First of all, you must adhere to COLREG. The abundance of the targets, which is often practical. If we are referring to the shipboard experience, I've often avoided collisions, or it's better to say I've taken part in the collision avoidance maneuvers with the 100 or more ships included in the China Sea. So the 5 targets is a little bit not enough, to my opinion. The diversity of targets characteristics, the estimated movement and the change of movement of the targets, and the plan B for the collision avoidance is also very important. For the better acceptance of the collision avoidance systems worldwide, I think that the standardization of the collision avoidance solution is necessary. And furthermore, there's a need for collision avoidance monitoring system. It should detect the need for amending the solution and the fast calculation of the amendment. As for the big data analysis, there is also a problem. The large amount of data, filtering and processing, data pipelining, the artificial intelligence systems, appliances. There's non-standard task and the human intervention and the standardization of solution packages for PTIS utilization. Based on this, we have some important challenges. The quality of decision-making or support systems needs to be assessed. The human factor and the staffing of semi-autonomous, not fully autonomous vessels, and the regulator or legal component of the process. If we have the decision support or decision-making systems installed, then we can talk about the autonomous navigation. From my view, the difference between autonomous and non-autonomous navigation is in implementation of various decision-making systems. So the concept of decision-making is always based on the choice of options, and the evaluation of this choice is not always transparent. It may often lack the link of to the physical reality. For example, the Bayesian networks, and at the same time, the decision-making systems can have good results. So, this approach for decision-making system resembles so-called black box system. It is not always convenient for users. The data is submitted to the input. The solution is issued at the output, and what happened to get it remains a mystery of the black box. At the same time, if human intervention is necessary, then for a quick understanding of the situation, such systems should be understandable and transparent for the operator. Of course, it's too unrealistic to expect a complete standardization of the decision-making. Scientific solutions are too many with various approaches of artificial intelligence and decision-making in general. At the same time, it is necessary to carry out the work in the field of harmonization of the methods for evaluating support systems and or decision-making. To do this, it is necessary to develop a widely applicable or universal approach to assessment. It is extremely important to observe the principle of unity of the assessment. The university has its own achievements and is ready to work in this field, but however, these are not complete yet. As for remote control, the ability to use VR and AR in the remote control conditions can be critically important for the obvious reasons. And so it's critically important to start developing appropriate solutions in the training right now. The value of this approach is also that it will be possible to evaluate the process for a wide audience and in the same conditions for the simulator or the real life. And we cannot skip the cybersecurity part. Cybersecurity naturally sounds like a separate issue here, but aspect of monitoring sensors as well as controlling the control of the vessel by the right person and not the wrong person, for example by the pirate comes to the first place. The university has already introduced elements of cybersecurity in the offered training, but it seems that this issue is becoming more and more important and should be further developed. In 2020, a consortium of leading transport universities in Russia was created, including this, our host university, the Russian University of Transport. The consortium areas of work include the following: development of autonomous navigation and maritime transport, and increasing the volume of international scientific and technical cooperation in the field of autonomous navigation. So the proposed formats of the international scientific and technical cooperations are presented in the slide. Namely, that is the creation of advisory groups or expert groups, including representatives of the world's leading scientific centers, implementation of autonomous navigation, also in seaports, development of training programs for specialists in the maritime industry to work with autonomous ships, creation of joint research teams working on agendas developed by advisory groups. And those are the proposed topics for discussion or works in these groups, and that is creation of specific training. Well, they're mentioned on the slide. I'll just read it. Development of international technical regulations for autonomous navigation systems, implementation of coastal infrastructure of a small and just any part of the operation remotely controlled at all autonomous modes. Implementation of real-time weather impact monitoring and implementation of data transmission networks for mass that are acceptable by all sides. Thank you for your attention, and I'm ready for your questions.
Okay, thank you very much, Vice Rector Stokley, for your very interesting presentation. For time limitation, only one question, okay? Question? Any question? Okay, for the time, now, thank you very much. Thank you.
Thank you very much.
Okay. Now let's welcome to next speaker from Aalto University, Dr. Borbot Victor. Dr. Victor is a postdoctoral researcher from Aalto University. His research topic is toward the safe autonomous navigation. Dr. Victor's main research direction include the safety analysis of complex and advanced marine systems, ship cybersecurity, novel autonomous system design, educational need for next generation autonomous shipping. Please welcome to Dr. Victor.
Okay, good afternoon, good morning. Can you see my screen? Can you hear me?
I think you should use play model.
Now it's in full screen model. Yes. Okay, excellent. So, good time of the day, distinguished delegates, ladies and gentlemen. My name is Victor, and I'm a postdoc at Aalto University. And today I will cover a topic related to safe autonomous navigation in this presentation. I will also present some information related to Aalto University and the project that Aalto University has been involved so far. I will also discuss why safety is important, especially in the context of autonomous shipping. And then I will suggest some ideas for how to ensure safety of navigation on ships. So, Aalto University has been established in 2010 by merging Helsinki School of Economics, Helsinki University of Technology, and the University of Art and Design Helsinki. It has 6 schools: the School of Arts and Design and Architecture, School of Chemical Engineering, School of Business, School of Electrical Engineering, School of Engineering, and School of Science. School of Engineering has a department related to the shipping industry. Aalto University currently has around 12,000 students and employs over 400 professors. It also has other 4,000 faculty staff. Aalto University is ranked as 112th university in the world, and it's considered as the 2nd top university in Finland, according to Q&S ranking. It is also ranked as 9th in the world among the young universities. 43% of the academic faculty is international. And this is something that I could see when I came to Aalto University. In our research group, we have people from Tunisia, we have people from Nepal, we have people from Mexico, China, Iran, New Zealand, and other countries. The Marine Technology Group currently has 7 professors and offer 6 different study paths. The first study path is related to Arctic marine technology, and the second study path is related to hydrodynamics. The third study path focuses on naval architecture. The fourth is related to project management. The fifth is related to smart maritime operation, and the sixth is related to structural design. Our group is ranked at 39th in the world according to Shanghai ranking on the subject of marine and ocean engineering. And it's the only Finnish university which is included in this list at the moment. We have 4 research groups related to different technologies. So we have a research group which focuses on Arctic technology. We also have a research group which focuses on hydrodynamics, structures, and marine systems. I belong to the research group on safe, which was working on safe and efficient marine systems. Aalto University so far has been involved in a number of research projects. One of them is the Alivesi research project, which was focusing on smart city ferries. This project has been completed in 2018, and it has offered some solutions and concepts for unmanned city ferries. The main partners involved into this project were the Norway University of Applied Sciences, Turku University, Aalto University, and the city of Turku. And the project received funding from a European Regional Development Fund. Additional financiers were the Finnish Transport Safety Agency and the cities of Helsinki and Espoo. In this project, topics related to the design of smart urban ferries were covered. We also investigated different concepts and services, the safety, the environmental aspects, and the testing of remote control center and remote operation. Automare is another project related to autonomous shipping. This project has been started in 2021, and its aims at developing a new educational solution required for educating next generation maritime experts. This project involves all of the Finnish universities which are working in the maritime field, and the financing is offered by the Finnish Ministry of Education and Culture. We have some specific objectives which are identifying the technologies which are used or can be used potentially on autonomous ships. We are trying to understand the impact of these technologies on the industry and the arising educational needs. They are also developing some pedagogical instruments which would support the future lecturers and professors at Aalto and other universities in training next generation experts. ECAMARIS is another project that has been recently started, and it's investigating the K-enabling technologies for mass. It involves partners such as VTT, ABB, Jim Robotics, AI Live Sim, and us. The financing for this project is offered by the Business of Finland. And we here in this project, we investigate concepts related to relocating the bridge, to conditionally periodically less manned bridge, and conditionally periodically unmanned bridges. Aalto University covers the aspects which are related to safety in this project. So, why safety is so important in the context of autonomous shipping? I think that we all are quite aware of the Boeing 737 MAX accident and the consequences of this accident. So essentially, due to some software issues and miscommunication between the aircraft systems and the pilots, we had 2 airplane crash. And we also observed that Boeing was obligated to land its fleet and this resulted in serious financial consequences. In other industry, like in aerospace, the improper interaction between system components has led to serious accidents and to failure of the mission. And this occurred in the case of Mars Surveyor lander crash and Schiaparelli lander in 2015. In autonomous shipping, we are using similar technologies which have been used in aviation and which has been using in aerospace industry. And therefore, these systems can be considered as complex, and complexity can result in unpredictable interactions. If these interactions are not properly identified and controlled, this can lead to some serious consequences in the maritime industry. So we can see a backlash from the public and people quite negatively reacting to the introduction of autonomous ships. And we can also see some serious delays in introduction of autonomous shipping. We have already observed a series of accidents in other industries, such as automotive. So we have seen some Tesla cars crashing, and this crashes resulted in some deaths of people involved in these accidents. We have also observed some incidences with autonomous trains in Japan, autonomous drone in Switzerland. Even small systems like autonomous vacuum cleaner, even this system have already caused some serious incidences and which required some surgical intervention. So I don't want to be a Cassandra, but I sincerely believe that it's just a matter of time when some sort of incidents will also occur in the maritime industry related to autonomous shipping. And the reason is that the systems are so complex, and it's highly likely that we will miss something, and this omission will lead to some serious issues. And issues which are related to the shipping are mostly related to the navigation. So we are talking about collision, contact, and grounding accidents, because these accidents can have some severe consequences. Just consider a scenario where an autonomous vessel, which is employing autonomous navigation system, is colliding with a small passenger vessel on a river or just outside the coast. And as previous incidences related to manned ships has taught us, this can lead to decades of losses. So in order to address this issue, I believe that we need to follow a life cycle based approach to tackling of the problem of safety. And in this approach, we need to start thinking about safety issues at the preliminary design stage, and we have to follow up the different requirements till the end of life for a vessel. So here we have to focus on the key enabling technologies, which are the situation awareness system, the collision avoidance system, remote control center, and the propulsion, which is necessary for navigation of the ship. On the right of the slide, I have also included the approach from NIST, which is can be also incorporated in a life cycle based approach. So it is necessary to identify the components which are critical from safety perspective. We need to protect them. We need to detect the different issues that can arise during the operation, and we need to respond and recover if the incident is occurring. So with respect to the preliminary design, we need to try to identify the issues as early as possible and desirably at a requirements level. And the reason is that the earlier we identify the design flaws and problems, the cheaper it will be to rectify the problem. 80% of the design problems can be covered at this stage. And if not a proper analysis is implemented at this stage, then some serious problems can arise later in the future. So with respect to the situation awareness system, it's critical to ensure that objects which can be encountered by the vessel are identified and they are fit to the recognition system. So the machine learning techniques that we are using, they have a whole spectrum of the objects that we can encounter during the operation of the vessel. But we also need to consider the impact of environment and on the system performance and the operational area characteristics and cybersecurity issue. With respect to collision avoidance algorithms, we need to consider which types of encounter situations will be allowed for use by collision avoidance system. But we also need to ensure that we have the proper ship hydrodynamics. We are following CORRIX, and we are taking also into account the cybersecurity issues. With respect to remote control center, we need to ensure the reliability of connections, the human performance in a new environment, the relevant cybersecurity issue, but we also need to consider the whole socio-technical perspective here and how it influences the human decision at the remote control center. And of course, with respect to the propulsion system, especially in case of unmanned vessel, we need to ensure proper reliability of the system. In the context of autonomous vessels, it is important to consider the functional and operational breakdowns and to try to work from bottom up. So it is good to follow the conquer and divide approach. But in this type of system, we can encounter situations which we call in safety engineering as emergent behaviors or black swans. So essentially, these are some situations where a properly designed system on a functional level is unsafe on a holistic level, because we did not consider how the function will interact with each other. And I'm just offering an example here on this slide. Here you can see a snowfall, and snowfall is developed by using some simple laws of nature, which are related to the freezing of water. But because of some variation in environment, these simple laws applied to water can result in a very complex structure depicted in a snowfall. And in the past, we have observed some accidents which were attributed exactly to this phenomenon, where we had a properly designed system which was designed according to the law, but because we missed some interactions between humans, organizations, and technology, we had some accidents. Here at Aalto, we are following some specific approaches which support us in identifying these interactions, and we are pushing the research further. With respect to the detailed design, we need to ensure that the detection system is accurate enough and that the objects are sufficiently and accurately identified. And this will guarantee us that the situation awareness system is working and it can be trusted. For the collision avoidance algorithms, we need to ensure that the hydrodynamic models are fit for the problem. And here I'm referring to the understanding of ship behavior in weather, wave, currents, and conditions, and also in shallow waters. some accident statistics have indicated that most of the accidents are occurring actually under bad weather conditions and bad base conditions, and when we have strong currents. While at the same time, the majority of the collision avoidance algorithms are being developed for use in still water conditions and under very nice weather conditions. That's why I believe that it's really necessary to ensure that the simulation testing, which I'm referring in the next slide, is considering the worst condition and not the best conditions. With respect to the remote control center, during the detailed design, it's necessary to consider the ergonomics, and it's necessary to use the reliable equipment and have redundancy in communication. And of course, with respect to the propulsion system, the architecture can be the key element. But the use of condition monitoring data can be also a solution to demonstrate that the reliability is adequate for the purpose. The verification and validation activities, I would anticipate them to be one of the largest challenges related to the safety assurance of autonomous vessel, because it can be quite difficult to test the systems under all potential scenarios that can be encountered by the vessel. And I believe that a gradual approach is required here, where when the systems are first tested in a simulated environment and then are tested under real conditions. But I also believe that here some risk-based criteria would be of a great help. I do believe that it might not be so necessary to test in such a depth small systems which are using autonomous technology. For instance, ships in harbors which are gathering garbages and are trying to ensure that we have clean water in ports. Because these systems, even something bad happens, they might not cause even serious fatalities to the people. But in the case of container ship with 20,000 TEU, I believe that more stringent requirements would be necessary for collision avoidance system. And the reason is that in case of loss or an accident for such a big vessel, then the damage can be much higher, and the financial consequences can be also more significant. Since we are talking about technology, which is new and we know very little, I believe that this technologies must be under strong scrutiny by the public authorities, and the public authorities needs to identify some monitoring methodologies for trying to identify the leader precursor indicators as much as early as possible. And by leading precursor indicators, I'm referring to some KPIs, key performance indicators, which are related to safety. They are not depicting accidents, but they're depicting some incidences, some small problems, but which combined with some inadvertent condition can lead us to accidents. Just an example is coming from aviation industry. In case of 737 MAX accidents, before these accidents even occurred, some of the pilots were having problems with this anti-stalling system. But luckily, in that cases, there was some experienced personnel which intervened and understood the cause of the problem and switched off the anti-stalling system. And hopefully, the aircraft managed to reach its destination safely. So this is just one sort of precursor, one of leading indicator. if this incident was reported to the authorities, then potentially the authorities could take some actions and could investigate the matter further, and we would have prevented the accidents that finally occurred. I believe that this is necessary to be implemented in the context of maritime industry as well, when talking about autonomous ships. It is also important to consider that since we are anticipating accidents to occur, we need to be ready for them. So in case of mass, we need to develop emergency procedures, which will ensure that even if something goes wrong, then we will manage to come back and we will restore the health of the system. Last but not least, we also need to take into account the recycling procedures. Since we are talking about software and information-intensive systems, it will be important to ensure that we have adequate procedures which would allow us not to leak some critical information about our system during the disposal stage. So in the future, it would not be so easy to scrap the vessel, because if you scrap a vessel which has some critical information about the crew and the personnel, then might be you will be sued by some people, which will be saying that you allowed for their personal information to be leaked to the third parties. So just concluding, I would like to emphasize that not considering safety early during the design and during the life cycle will cost, and it is important to include the safety in the different life cycle processes. And during the initial design phases, it's important to consider proper requirements and complete set of requirements. During the design, we need to follow up these requirements and to trace them. During the verification, we need to verify them and test to the adequate depth. During the operation, we need to check whether the requirements are actually followed by the design. And during the design disposal phase, we need to ensure that critical information is erased from the ship system. I would like to thank you for your attention. And if you have any questions, you can proceed now, but you can also contact me or my supervisor through the emails that you can see on the screen. Thank you very much.
Okay, thank you very much, Dr. Victor, for your interesting presentation. Do you have any questions?
Mm-hmm.
Okay.
I can see one question in the chat.
Yes.
I will read it loud. Interesting. I'm Kun Long Fan from South Marine Science and Engineering Lab, Zuhai. Thank you for your presentation. I have a question to ask. For safety of navigation, do you consider other accidents not limited to collision? To mass a high-tech ship, it may be smart to avoid collisions in some scenarios, but how to avoid other kinds of maritime accidents or incidents at near misses, for instance, fire, grounding? That's a very good question, Mr. Kulongfan. Thank you for asking it. Actually, the answer should be structured around the different autonomous degree which are used by IMO. So if we focus on autonomous ships which have some crew, so I'm talking about autonomous degree 1 and 2, then we are not going to face such problems because the crew will be available on a ship, and they might be intervene in case of fire and even in case of grounding. But if we are talking about completely unmanned ships, so autonomous degree 3 or 4, then in such cases, it might be a very big challenge to tackle exactly these issues. Fire, for instance, fire. I need to be honest. I'm quite skeptical that we will see unmanned 20,000 TEU container ships operating in open ocean in foreseeable future, and this is exactly for these reasons, because I don't believe that a ship operating company will decide to save some little cost related to operating crew in order to expose the ship to the risk of fire. And just imagine if you have one container which is, you cannot control what is in this container. You just know it from out of based on the bill of lading, and there may be some batteries or maybe something else, and then these batteries just take fire, and there is no crew to extinguish fire, and all the other containers get fire as well. We are talking about serious damage, and I'm quite skeptical that ship operating companies would take such a risk and would allow big ocean-going vessel to operate fully unmanned.
Okay, thank you for your answer. Thank you. Today's presentation is all finished. Now we turn to the closed section. 好，下面首先请容许我代表。
First of all, on behalf of our venue, I'm going to give a speech on behalf of Wuhan University of Technology. We have simultaneous interpretation here, right?
Hello， 请问一下同传在吗？
He was asking if interpreters are there, but apparently he cannot hear me. So can someone tell him that interpreter is ready? Thank you so much. So on behalf of Wuhan University of Technology, I'm going to express my thanks. First of all, our conference today is very successful. And thank you so much, all of the organizers and all of the participants and all of the speakers, presenters, and all of the guests, representatives, and expert scholars present here. Thank you so much for being part of today's conversation. And this conference is also very, very widely influential within our circle. We hope that this conference will play a bigger role in our circle in the future. And so this is why our university is going to participate in this conference next year. And I also hope that all of you can also join us yet again, no matter we're going to meet in person or meet online. We hope that we can see your faces again next year. Lastly, as for the initiative, well, we're going to support this initiative. We're also going to translate that into reality. And we also hope that everybody can be actively involved here. And then I'm going to give the floor to Harbin to give their closing remarks.
最后的这个讲话。那么，女士们、先生们，各位专家，大家好。经过2天的充实的会议，我们第5
Ladies and
届
gentlemen, dear experts, after 1.5 days fruitful discussion, our international conference of naval architecture and marine engineering, aka the International High-Level Forum on Smart and Autonomous Navigation Technology of Ships, has been successfully concluded. Let me thank all the staff of the organizing committee for your contribution for making this conference possible. We have 3 offline venues and as well as an online Zoom conference room. This conference is also broadcast to across the whole world. We also have other forums covering various topics, including education and youth and the technologies. We have listened to 31 keynote reports, and the reports have shared with us various contents related to mass technologies covering unmanned, green, low carbon ships, as well as unmanned ships. These are all the advanced and hot topics in the industry. Our offline venues have witnessed over thousands of attendees, and online there have been over 3,000 members of the audience. You can see that this conference has received wide attention. What's worth noticing is that Madam Heike Degim also attended our forum and delivered a speech. We are very honored. And we also had experts from the RUT, from Korea, and Wuhan University of Technologies. They all shared with us, experts from various countries shared with us their perspectives and their research. We've shared our experience in all these advanced fields, and universities carried out a very active discussion over these technology-related issues, as well as resource sharing and cooperation in education. On behalf of our organizers from the RUT, as well as HUT and HEU, we together initiate the International Joint Lab on Mass Technology. And after this conference, we're going to continue to promote the joint lab, and by the end of this year, we're going to make major progress. And the universities, for example, from Seoul, from Norway, from Finland, if you are, we've already received their wish to join the lab, but some procedures have to be carried out at the school level, at the university level before they actually join us, and there will be open link given to you with the materials emailed, and you're all very welcome to join us. During this conference, we have reached a great agreement over the outlook of mass technologies, and we can also feel that there are technological challenges. For example, our detection of the environment and the accuracy in communication, and then cybersecurity, information, and decision-making, etc., etc. Challenges are everywhere. So in front of these challenges, I believe it's necessary that universities across the world should join hands together to tackle these major difficulties so as to promote the mass technology development around the world. Currently, COVID-19 has inflicted great pain on us. We cannot see each other face to face, but this is not hindering us from working together. It is fair to say that we all harvested a lot from this conference. We are looking forward to the future where after COVID-19, we can meet each other face to face and share with each other our research results. And we sincerely welcome our colleagues in the universities overseas to come to China, to come to HUT or HEU, WUT or HEU to discuss further our meeting, our cooperation. And finally, please allow me to announce the successful conclusion of both the international conference and the high-level forum. Thank you very much.